it. But homework, let's talk about homework just to see if there are any residual issues with the homework. Wait, is this? Nope, that's not homework. Where is the homework? Here it is. So here's the homework. So this was on arc length. So what sort of arc length issues did you have? And then we can do the quiz. You can, of course, do the quiz at your leisure if you're bored. Um, but, uh, but we'll see if there are any questions about. Yes, what do you think, Michael? Yeah, let's take a look at these. So probably you're just going to have to, yeah, 16, yeah. Let's take a look at both of these. I should have previewed this and figured this one out on my own, but yeah, 14 is kind of interesting. So let's do that one first, and then we will do 16. So you know the drill. We're going to do the derivative of this thing, and the derivative is going to be 1 over the cosine times the derivative of cosine, which is the negative sine. So there it is. So take a minute, make sure that if you believe what I have there, then we can move on. Okay, now that we've got that out of the way, no one's complaining. Let's see, I need my limits. Here, I'll just keep the limits over in the bottom corner. So we're going to set up this integral like this, square root of 1 plus that thing squared. And let me just point out that that is the same as the negative tangent of x. So I don't know if you noticed that, but that's the negative tangent. Um, so anyway, this will be tangent squared, because you're squaring it. Welcome. Oh, yeah, I guess I don't think I gave quizzes to everyone. I'll get you the quiz, not to worry. We're not, yeah, just if you came in and you didn't have a quiz and you're jealous of your friends, I have extras. I'll get those to you in a bit. So don't worry. But anyway, getting back to this, now the rest of this is really straightforward. This is going to be the integral from 0 to pi over 3 of the square root of secant squared. Okay, so whenever we have trig functions, you should expect that you're going to end up doing some sort of, oh, that color is bad up there on the screen, isn't it? You're going to have to use some sort of identities, and hopefully you've seen enough of these to recognize the 1 plus tangent squared is the same as secant squared. If not, here it is. And then the square root of secant squared is the absolute value of secant, but for this range of values, the secant is always positive. So we're just going to go with this as this. No. Let me do it right. Okay, I suspect that you won't do that, but technically, when you square something and then you do the square root, you get the absolute value of that thing that you squared. Secant squared, sorry. There, is that what you, yeah, that's better. So, but in this case, if you think about the angles that we're talking about from 0 to pi over 3, the secant is positive for all of those angles. And so the absolute value will just be the same as the secant. Otherwise, we would have to deal with a negative somewhere, but this is going to be fine. So this is 0 to pi over 3 of secant of x dx. And now we have to figure out what that is, but we did this once before. I'm not going to do it again. That's going to be the natural log of secant x plus tangent of x. Wait, is that right? I believe so. Oh, now I'm doubting myself. Is it? Just a minute. Let me double check. That is right. Oh, good. So, by the way, yeah, this is the sort of thing that I did when I was taking calculus 40 years ago. I would be like, oh, is that really right? And so then I'd have to rederive the formula. Here, just in case if you don't believe me, you can do this plus tangent secant plus tangent, and then you let u equal secant plus tangent, and you find that du is this stuff up here. So that's why it's that. Okay, now that we're good, let's go ahead and plug and chug this answer out. So first of all, the top natural log of the secant, okay, I'll write it out. The secant of pi over 3, which happens to be 2. We all know that, right? And then the tangent of pi over 3, which is radical 3 over 2. Oh, whoa, whoa, whoa. No. Just radical 3. Sorry. So this will be the natural log of 2 plus radical 3. I'll just put parentheses. Oh, sorry, I forgot my lower limit. Oh, what a rookie mistake. Pull this down here. Lower limit minus natural log of the secant of 0 plus the tangent of 0. I guess it doesn't matter that I forgot it because that's the natural log of 1, which is 0. All right, so for Michael saying, the trig functions are hard, you're right, they are hard. Everyone hates them, including myself, just so you know. Actually, that's not true. I kind of like them because they're hard and I like a challenge. But yeah, there it is. Okay, let's take a look at this next one. Where did it go? There it is, the hyperbolic cosine. So the main issue here is what the heck is a hyperbolic cosine, right? So let's do that. First of all, the derivative of the hyperbolic cosine is the hyperbolic sine. And then you use the chain rule to multiply and you get just hyperbolic sine. What is the hyperbolic sine or the hyperbolic cosine? Well, that's a different lesson. So if you really want to know, let's see, the gateway arch is a hyperbolic cosine. I don't know if there are any hyperbolic sines that I can point to in nature, but at least you got the gateway arch for, it's not a parabola, it's a hyperbolic cosine. But getting back to this, let's go ahead and crank this into our formula. So here, I'm just going to write this down here. So this will be the integral from 0 to 1 of the square root of 1 plus the hyperbolic sine squared. So let me pause for a minute, make sure that makes sense. Any complaints, questions, worries, fears? Not all that. Okay, so next, let's deal with this thing. So you probably are familiar with the not the hyperbolic, the regular sine and cosine identities, but there are similar identities for the hyperbolic sine and cosine. In particular, if you take the hyperbolic cosine of u, square it, and add to it, subtract the hyperbolic sine, you get 1. So that's the difference between the hyperbolic sine and cosine. And by the way, it's fascinating. I'm sure there's got to be a YouTube video that explains the hyperbolic functions. I do a lesson in some class. Maybe I don't do a lesson in this. I used to. I used to do a lesson back when we did, how our book is early transcendentals? The old version, like 10 years ago, I used to use the non-early transcendentals, and we would go over hyperbolic functions in Calculus 2. And so, I don't know, if you really want me to, I can pull that up. We can talk about, catenaries. But getting back to this. So yeah, by the way, here, let me just give you a quick overview. Hyperbolic cosine, I might have written this down before, is e to the u plus e to the negative u over 2. It's the average of those two exponential functions. And the hyperbolic sine is e to the u minus e to the negative u over 2. And you know how, here's one last thing. You know how in a unit circle, if you draw the coordinates of this point are the hyperbolic sine and the hyperbolic cosine of the angle. Well, if you draw, instead of a circle, if you draw a hyperbola, then the coordinates of that point are the hyperbolic sine or hyperbolic cosine and hyperbolic sine, not of the angle, but of this arc here. So whatever that is, because the angle is the same as the arc with a unit circle. So it's this distance. So you take that distance, and that's what we call the hyperbolic sine and cosine. Okay, whatever. I know. That was a super fast version of where are we getting this hyperbolic sine and cosine from? But anyway, there it is. So we're going to use this. So the hyperbolic sine is equal to the hyperbolic cosine minus 1, so, or squared. Hyperbolic sine squared is hyperbolic cosine squared minus 1. So this thing becomes this, 1 plus hyperbolic cosine squared of 2x minus 1. You can see what's going to happen is this will give us lots of joy because you'll have just the square root of the hyperbolic cosine squared, which is just the hyperbolic cosine, 2x, sorry. And that's easy enough. The integral of the hyperbolic cosine is the hyperbolic sine, just like, sines and cosines. It works very similar. So this will be 1/2 times the hyperbolic sine of 2x, evaluated from 0 to 1. And so you just end up with 1/2 times the hyperbolic sine of 2. And if you want to know what is that, well, that ends up being, sorry, I've run out of room somewhere. So that's 1/2 times 1/2 e to the second plus e to the negative second. Minus, sorry, it's a minus there. By the way, your calculators, if you have one of these, you actually have hyperbolic sine and cosine on it. It's just not one of the keys that you would press. What you're going to do is you're going to take this calculator and press the catalog button. Where is catalog? It is, what in the world? Oh, there it is. On my calculator, it is second 0. So second 0. And then you see that you have a long list of functions. And I think you can just press the, what are we looking for? Hyperbolic sine. So press the S button, which is, it's so hard to read all of these little letters there. Okay, I found it. It's the natural log button, has a S above it. And then go down far enough, you'll find hyperbolic sine. There it is. I found it. I know you can't see, but there it is. And then I can do the hyperbolic sine of 2 divided by 2. And my decimal answer is 1.8134 for what it's worth. Wow, probably way more than Michael wanted. So you can thank Michael for that long, lengthy answer. Sometimes I get a little too excited, especially when we talk about catenaries. So what else do we need to talk about with the arc length? Can you do arc length? Okay, Eli, what's going on? All right, what about number 11 is a problem? Like, you got it set up, or is it the algebra? Get that algebra done. Yeah, this one. Yeah, this is one of those similar to what we did. Remember the one in class that worked out nice? Well, I should say nicely in quotes, because some of you might be like, that was ugly. So give me a sec. I just want to copy this and put it down lower so that I have more room. So let's see. Copy and delete. Okay. That'll give me a chance to plunk it down here. Ooh, there's a catenary. Sorry. Yeah, any a cable that's hanging between two. That's the same as, it's an upside down gateway arch. Okay, but getting down here, let's paste this in here. Whoops, there it is. So so Eli, you know that this is going to be x squared minus 1 over 4x squared. Is that right for the? And then you can set this up. It's not all that hard. We're going from 1 to 2. Sorry, get rid of that 0 there. I'm just so used to having the lower limit be 0. Square root of 1 plus x squared minus 1 over 4x squared squared. So this isn't a problem. It's getting that simplification. So let me go ahead and do the simplification for you. I'll do it rather quickly, though, just to warn you. I'll try to explain all the different bits, though. So step one is you're going to square that binomial. So, whoops, there we go. So square that binomial. So we've got x to the fourth minus 1/2 plus 1 over 16x to the fourth. This is such a useful thing to know. I'm going to write it down. There. Whenever I square a binomial, that's what I'm thinking in my head, is you take the first thing, square it, you do twice the product of the two things, and so you have a negative here, that's why that's negative, and then you do the second thing squared. So it's just so useful, it makes things so quick. And then here you get this, x to the fourth plus 1/2 plus 1 over 16x to the fourth. Now at this stage, you probably would be more comfortable writing this with a common denominator. However, given the fact that we just squared that binomial and got that, I think that we all could be a little suspicious about the form of this thing and the factors. And so let me just go ahead and write down what the factors are without going through the trouble of doing the common denominator and all that. So like I said, last time, so on yesterday, I did one like this where we wrote down the common denominator, combined everything, and then factored. But you can double check if you don't believe me. Square this, and you get this. So, and the reason why I'm so suspicious that this would be the case is because we just did that. And so it looks so similar. But anyway, once you have that, the rest of this is just going to fall out in your laps. So I don't know that we need to work through the rest. But here, I'll just do this one more thing just to show you. 1/4 x to the negative 2. There it is. So when you square that, technically you would want to put an absolute value around this, but notice what we have here. X squared is always positive. Here, 1 over 4x squared will always be positive. So if you put an absolute value around there, it's unnecessary because you're dealing with all positive numbers. So then the rest of this you could probably do, yeah. So the algebra is hard at times. And honestly, I know that especially for you engineers, here's what you're most interested in right there. Yeah, this. Getting it set up, because once you have it set up, if you're an engineer, you're probably just going to pull up whatever software you're using and you're going to crank it in, or you use your calculator to figure out the answer for that arc length. So anything else from this homework that we need to look at? All right, well, let me make sure everyone gets a quiz because it's the day before an exam. I won't be collecting this. Who needs one that I neglected? You need one, Christian. All right. Anyone else that I neglected? Okay, thank you, Andy. Here, you want one? And I'll fix the attendance while you're working on this. Oh, okay. So I'll put it up on the screen for those who are absent. Give me a sec. There we go. Okay. Oh, huh. I'm not going to give you a ton of time to do this just because some of you already finished. So I don't want to bore you. All right, for the sake of those who have finished, let's go ahead and set this up. It won't take too long, and then we can move on and talk about the practice test. So let me know if you have questions about this, but I'll just go ahead and first of all set this up. I guess I need to do this. So f prime is 3/2 times 1 plus 2x to the 1/2 times 2. Okay, that's really ugly, isn't it? It's 3 times the square root of 1 plus 2x. How's that? Okay, so now that we've got that out of the way, let's move this down here. The arc length is going to equal this, this integral of the square root of 1 plus that thing squared. Okay, 3 to 37. And by the way, just a quick note. Here, I'll write this down. Here. Let's see. Since this seems to be popping up pretty often, this there. If you have something and you square it, then you do the square root. You get the absolute value of that thing. However, if you have the square root of something and you square it, you get that. But the issue here is that a has to be bigger than or equal to 0. So, because up here, you can stick a negative number into that thing, the square root of a squared. That's fine. You cannot put a negative number into that second thing. So whenever I do this, so you see I've squared a square root, I have to at least acknowledge, I suppose, that 1 plus 2x is bigger than 0, or non-negative rather, which it is. I mean, look at the range of values. I have no negatives there, so none of the x's that I'm going to plug into this will be a problem. Okay, now let's crank this out. The rest of this is pretty straightforward. 37, square root of, this is going to be what, 10 plus 18x. Did I get that right? Okay, then do the antiderivative. So 1 over 18. You could do, what is it called? Substitution if you need to, but there we go. This is evaluated from 3 to 37. Did I get that right? Does that look okay? So this is 10 plus 18x to the 1/2 power, so it becomes 3/2 power. And then if you did do the substitution, which we've done this so many times that I feel like linear functions, I've gotten so used to just ignoring the fact that it is a substitution, at least for like in Calc 1, I wouldn't do this, but I think you're sophisticated enough. You can just do that. Then let's go ahead and plug in our numbers. So that's going to be 1 over 27 times 10 plus 18 times 37 to the 3/2 minus 1/27 times 10 plus 18 times 3 to the 37. 18 times 3 is what, 54? So that's, 64. Whoops. I don't know why I put a 37 up there. So that's 64. Interesting. And 64 is a perfect square. I wonder if the other number is a perfect square as well. Let me find my calculator. Put it over here. I very well know the answer. So, well, I know the final answer, but so 10 plus 18 times 37, 676 is a perfect square as well. Amazing. Whoever came up with this problem must have been really smart. They're watching on the, so confusing. Is this thing working? Reconnected. Sorry. So people watching on the video are going to miss that little quip about the 676. That's probably better. Okay, so 676, let's do to the 3/2 power. Minus 64 to the 3/2 power. And because these are perfect squares, it's going to come out to a nice number. So that is 17064 over 27, which is 632. Is that right? 27. 632. Amazing. Okay. So I always, I always try to make it come out nicely, and it sometimes does. So very nice. So there's the quiz. So any other questions about how that's done? There we go. No one's begging for mercy. So let's go back here. So before class began, someone told me, I forget who, pointed out that I had a mistake on my alleged answers. So I'm going to be correcting them. But just so you know, this file is called Calc2 alleged answers. And the mistake was, it's right here, number 6, compute the average value, which whenever I got to be honest, I did this last year. This is the same practice test I gave to last year's class. And I probably was thinking about probability because this is the formula for the expected value or the average value of a probability distribution. So, so anyway, I have a corrected version that I'm working on. So any other, there was also a blank one that didn't get done for whatever reason. So this will be the corrected version that I will upload after class today. But you'll see I've left this blank now. And so let's go ahead and do this since it's not all that hard to do. Just to remind you, the average value of a function, you do 1 over the distance 2 minus 0 times the integral. So this is going to be 8x squared minus 4x cubed. So 1/2 times, let's see, 8x squared is going to be 8/3 x cubed minus x to the 4th, evaluated from 0 to 2. And so this will be 1/2 times, what's that going to be? 8 times 8 is 64/3 minus 16. 64/3 minus 16, which is 64/4. So that's going to be 64/12. So 1/2 times 64/12, which I can simplify, I realize, 16/3, 8/3. Is that the right answer? I don't know, whoever it was that complained. Oh, you did it? And this is what you got? All right, I'm happier now. Good. And I'm happy that I know all my fractions as well. Okay, very good. All right, so that takes care of that one. The other one that I didn't have filled out, but I do on this version magically, is this over here. It's there it is, number 10. So there's the whole thing, the long division, the quotient and remainder of that function. So if you were to, the whole point of doing long division is if you were going to do the antiderivative of this, you would first do the long division and do the antiderivative of this. And probably do some sort of substitution here. I don't know. I don't want to do that. So, okay, so there's that. So let's see. I can show you. I showed people earlier the actual exam. I can show it to you as well. Let's see. I'll pull it up just so you can see what it looks like. Here it is. Oh, there it is. Yeah, there it is. Beautiful, isn't it? So you can see sort of the scope of what's going on. Not very complicated. It's not going to be terribly difficult. Hopefully, it won't take you forever. But you can see that there is a quotient and remainder. So pretty clearly, right there. So make sure you can do that long division. And then there are a few of these partial fractions problems. So make sure you can do those as well. So getting back to the practice test, were there other places that you might have seen like issues so that I can fix them before we before Friday? Or are you just worried? You just want to know, is such and such on the test? I know how you are. You're like when I'm in a faculty meeting and someone asks if they have any questions, I always hope. I hope no one does, because it would mean that we can get done early. Michael, though, in the back, you have a question? Now everyone's mad at you. No, I'm just kidding. So what's up? It's always better because maybe everyone has the same question. What's going on? What I tell people usually is that a good way to study is to look at the practice test and to look at the quizzes. So what I do is usually I'll take like questions from the quizzes and put them on the test, and then I move some things around and change some things. So like this arc length, which I don't think shows up on here, but just be sure you know how to do it. I would take that, stick it on there, and then change the function a little bit. Probably make it into a nice linear function. Like if that was f of x equals just 1 plus 2x, it would be so easy. It would take you almost no time. Just so you know the form of it. Yeah, but yeah, if you study this, that's pretty much all of it. So I hesitate to say that it's identical to this. These are old test problems, and there might be a question that's not quite like those. But if you know this, I think you'll be fine. Yeah, other things, other worries and fears. Wow, you're better than, no, not better. You're less talkative than statistics was. Okay, I have a couple of instructions, and then we'll be all done. First of all, I have a couple of volleyball players. I don't know if any of you are volleyball players. No one's going, oh, you are. Oh, that's right. Oh, you are too? Okay, who claim, we'll see if this is true, that they have to leave early on Friday. This is true? Okay, so here's what my volleyball players are doing from differential equations. They're going to show up in this room at 7:15. That's how tough they are. It's 7:15 on Friday. They're going to be here to take their differential equations test. So if you want to, and this is for anyone, even if you don't play volleyball, you want to come at 7:15? Be my guest. I'll be here at 7:15 to start the party with at least the volleyball players and maybe some of you. Of course, you know that I'm going to have an exam in this room the hour before. So 7:50 to 8:50, I'll be here. And then, so if you want to, you could potentially come at 7:15 and work until 10:15. I can't imagine spending 3 hours on this test. But you want to fly under the radar, you just come, sit down. I won't notice that you're spending 3 hours, to be honest. I'll just be like, here's your test. And then at the end. So you want to come early, great. If not, yeah, I will want to try to collect it by about 10:15. So just be aware of that. One more thing before you leave. I had a colleague, so you're probably familiar or have heard, we have these budget cuts that have happened, and have several colleagues who, good friends of mine, who have been told they aren't going to be here next year. So one of my colleagues said that they would really like to have a t-shirt. And I was like, oh, okay, I'll make a t-shirt. So I made t-shirts, and now I've got like 60 t-shirts in my office. I'm like, what am I supposed to do with these? So I've given some to like certain people, but if you want one, I paid $15 for these, but I'll take 10 or 5, whatever you can pay. They just have the names of the various. So if you have your favorite professor that you love who isn't going to be here next year and you want to wear a shirt, There it is. I have my Venmo information here, or you can give me cash. I only have larges and extra larges, not because I made that choice. I was talking with another colleague who said, oh, you don't need to get smalls and mediums. This is a female colleague, by the way. She said, yeah, you got a fat kid, they're not going to be able to squeeze into a small, but a skinny kid can take a large or an extra large fine. So I do have a couple of mediums that I did get in my office. So if you really want a medium, you can have it. But yeah, so if you want to give me money, great. If you don't, that's fine too. But I kind of would like to recoup a little bit of the money I spent. So that's over there. That's it. I'm going to pause this recording. I will be here. Oh, for the people who are watching, I will be here tomorrow, of course. Just let me know so I don't wander off. But I have all day. So if you have second thoughts about questions, come tomorrow.